I will continue my lecture on heat utilization in furnaces. Today, I will be illustrating role of heat recovery devices. As already we have learned that heat recovery devices are the devices which recover the heat. In this connection, the efficiency of heat recovery devices is important. Unless they are able to recover a high amount of heat, they will not be able to impart that heat to, for example, incoming air. So, we have also seen the relative efficiency and efficiency limit of the heat recovery devices. We have defined all those things and we have learned the concept and how to use these heat recovery devices. Now, I have also said that there are two important heat recovery devices. One is the regenerator, another is the recuperator. Which one will be suitable? That will depend upon the temperature of the discharge gases. If the temperature of the discharge gases is very high, for example, of the order of 800, 1000 or 1200 degrees Celsius, then the recuperator is not useful, because recuperator, their essential construction is that of metallic part. However, for higher temperatures, regenerators are used, and regenerators essentially they have brick checker work. In that, hot flue gas are allowed to flow, and in that first cycle, when the hot flue gases flow, the brick checker work gets heated up. In the next cycle, air passes and it recovers the heat from the brick checker work and gets heated up. So, essentially regenerator or recuperator both are heat exchange devices. So, today I will be illustrating the efficiencies of heat recovery devices and their integration with the furnace. As I have also said that it is very important to integrate the furnace with the heat recovery devices, because heat recovery devices will essentially heat the air and that air will pass to the furnace. So, let me illustrate it with an example. I will consider say case 1. Let us consider a furnace. Consider a furnace integrated with a regenerator. The furnace uses fuel oil of composition 90% carbon and 10% hydrogen. This fuel is burnt with 110% theoretical air. In the case 1, we observe no air leakage. So, no leakage of air, to furnace. We also assume that the relative efficiency of the regenerator efficiency of the regenerator is 80%. So now let us calculate for this case. Let us calculate gross available heat for this case and understand the concept of different efficiencies which I have introduced in my earlier lecture in order to calculate gross available heat. Later on, we can also correlate this with the fuel consumption and as well as fuel saving. Let us see. So, the same thing I will be representing in a block diagram, and the block diagram is this way. Say this I will consider as a furnace which is operated such that the flue gas temperature is 1371 degrees Celsius. So, invoking the concept of critical process temperature, we assume that the furnace is operating at 1371 degrees Celsius. So, as such flue gases are also discharged at 1371 degrees Celsius. That is what the concept of critical process temperature means. You should also understand that a critical process temperature similar to flue gas temperature, that means a very uniform heating. It is an idealized representation of the problem. In actual practice, this may not happen. In actual practice, the flue gas temperature may be somewhat lower or may be somewhat greater, which depends on the rate of heat demand, as I have illustrated. But for the sake of illustration, let us take critical process temperature is that of the flue gas temperature. So, here the flue gases. So, now the inputs are, we have fuel oil whose composition 90% carbon, 10% hydrogen, and this is burnt with 110% theoretical air. We have also assumed that in this case no air leakage. No air leakage. And now we are integrating it with the so called regenerator. So, this is a regenerator which will be heated by the heat of the flue gas, and later on the cooled flue gas will be discharged. Now, we are also considering that all the 110% theoretical air is being preheated, and this preheated air is supplied to the furnace. So, since there is no air leakage in the furnace, so all 110% theoretical air, it will be preheated through a regenerator, and that preheated air will be transferred to the furnace. So, what we are assuming here, so all air here 110% is preheated. So, essentially we are supplying here preheated air into the furnace. So, if we want to calculate the gross available heat, as I have repeatedly said in my earlier lectures on combustion, that is lecture 9 to 13, the first and the foremost requirement of doing heat balance or calculating anything which relates to gross available heat or net available heat, material balance is most important. So, first we have to do material balance. material balance. We will assume there is complete combustion. There is complete combustion, that is, there is no CO formation in the flue gas. Now, we have to perform the material balance, and for that basis we will be using say 1 kg fuel. Well, I will not do here for you material balance calculation, since we have already done this exercise in earlier lectures. We should understand those and try to do material balance, like 1 kg of the fuel, do the carbon, find out the stoichiometric reactions and write down the various products of combustion. So, I have done for you, and what I am straight away writing the products of combustion, or they are also called flue gas, both are one and the same thing. It is a carbonaceous fuel, it contains carbon and hydrogen, and it is burnt with excess air, and our assumption is complete combustion. So, that tells us straight away that the products of combustion will consist of CO2, H2O, nitrogen, and since there is an excess air, so there will be oxygen also in the flue gas. So, I am calculating in kg moles. CO2 is 0.075 kg moles, H2O 0.05 kg mole, nitrogen 0.4136 kg moles, and oxygen is 0.01. So, we have this material balance before us. Well, in terms of percentage, so the total POC is 0.5486, 0.5486 total POC. So, percentage will be 13.7% carbon dioxide, 9.1% H2O, 75.4% nitrogen, and 1.8% oxygen. So, we know now this is our POC composition, and this particular flue gas, it consists of, here now we can straight away write down here that CO2, H2O, N2 and O2 of the respective moles, say 0.075, 0.05, 0.4136 and 0.01, they will be entering to the regenerator, and the output will also be CO2, H2O, N2 and O2. CO2 will also be, since they are not consumed, so their moles will remain the same, 0.4136 and 0.01. Since when these moles of flue gas, they are passed into the regenerator, remember moles are not at all consumed, it is the only heat transfer occurs only on passing through the regenerator. The flue gas which exits the regenerator will have a temperature lower than the entry temperature of flue gas. So, further we calculate, we also will be needing the amount of dry air. So, we calculate now amount of dry air, So, first we can calculate the theoretical amount of air, simply C plus O2 CO2, all of you know, theoretical air, or if you have any problem in calculation, refer to my lecture 9 to 12. Theoretical air, that will be equal to 0.476 kg mole and since 110% excess air is used, so the actual used air that will be equal to 0.5236 kg moles. So now we have a complete material balance before us. We know that much amount of air would be required, and that much amount of air will be preheated into the regenerator. That much amount of flue gas will pass into the regenerator. Now we are in a position to calculate heat related quantities. So we have to calculate now gross available heat. Gross available heat, and as you all know, gross available heat that will be equal to calorific value of fuel, plus sensible heat in air, minus heat to products of combustion or flue gas, both refer to the same meaning, should not confuse in any way. So now, in order to calculate gross available heat, we should know what is the calorific value of the fuel. Now, if calorific value of the fuel is not given, then calorific value of the fuel can be calculated by the so called Dulong formula, which I have done in the lecture number 2. So, the calorific value, if I use the Dulong formula, then the calorific value of fuel, that is equal to 10,642 kilocalorie per kg. Now we have to calculate sensible heat in air, because air is preheated in the regenerator. So first we will have to calculate the so called sensible heat in preheated air. Sensible heat in preheated air. Now for all calculation on heat, our assumption, say basis of calculation, as I pointed out at several places, is 25 degree is our base temperature. That should be clear. So now sensible heat in preheated air, it can be calculated by the various efficiencies which we have defined in the earlier lecture. So if you recall, we have defined the so called efficiency limit. So this efficiency limit, I am writing once again, efficiency limit that is equal to sensible heat in air at hot flue gas temperature, and in our case the hot flue gas temperature is 1371 degrees Celsius. I am straight away writing upon sensible heat in POC at same temperature. That is the efficiency limit. So here first of all we have to find out what is the sensible heat in POC at 1371 degrees Celsius, or sensible heat in POC means how much amount of heat POC is taking with it. So, we have to calculate now the heat to POC or sensible heat in POC. So, now we have to calculate heat to POC. Heat to POC. Very straightforward, mCp into delta T. You can calculate taking Cp is equal to A plus 2Bt plus C by T square, as already I said, or for easy calculation in order to illustrate what I am using, I will be writing here the enthalpy content at the temperature of interest on the basis of reference temperature. So, I am writing here the enthalpy content, for example, H 1644 Kelvin minus H 298 for CO2, that is equal to 16834 kilocalorie per kg mole. Similarly, H 1644 Kelvin minus H 298 H2O vapor, that is equal to 13168 kilocalorie per kg mole. Then H 1644 minus H 298 nitrogen, that is equal to 10389 kilocalorie per kg mole, and H 1644 minus H 298 O2, that is equal to 11,000 kilocalorie. Now, straight away we can calculate heat to POC. All that you have to multiply kg mole with the respective enthalpy content. So, heat to POC, that will be equal to 0.075 into 16834 plus 0.05 into 13168 plus 0.4136 into 10389 plus 0.01 into 11,000. So, if I sum total it, then this will give me heat to POC 6328 kilocalories. Now, similarly, I know now the amount of air. Air consists of 79% nitrogen, 21% oxygen. So, I can also calculate now the sensible heat in air, sensible heat in air at 1371 degrees Celsius, that will be equal to 0.4136 into 10389 plus 0.11 into 11,000. So, this is the sensible heat in air at 1371 degrees Celsius. So, that will be equal to 5507 kilocalories. So, now I can calculate the efficiency limit. So, you take the calculator and calculate it, that will be equal to 5507 upon 6328 into 100. So, that will be giving you 87%. This is the 87% is the efficiency limit of the regenerator. Now, I can calculate the so called overall thermal efficiency. Overall thermal efficiency, you know, that is equal to efficiency limit into relative efficiency. So, if I do that, efficiency limit is 87%, relative efficiency is given to 80, and if I divide by 100, now this 80% relative efficiency is given. So, that is equal to 69.6%. So, this overall thermal efficiency of 69.6% tells you that only 69.6% of the heat of the flue gas will be available to preheated air. That is the meaning of overall thermal efficiency. So, in this particular problem, the heat transferred to air, heat transferred to air as the amount of air passes through the regenerator, that will be equal to 0.696 into 6328, and that will be equal to 4402 kilocalorie. So, this is how you will be calculating the amount of heat that is obtained when the amount of air passes through the regenerator. Now, if we consider the heat balance of a regenerator only, then the following picture emerges. So, now we consider the heat balance of regenerator. Heat balance of regenerator. Again, I draw a black box. So, that is a regenerator. Amount of heat which is entering 6328 kilocalorie. Now, we consider now, let us say 10% of the heat input is lost. 10% of heat input is lost. That means 632 kilocalorie is lost. We could recover 4400 kilocalorie is recovered in the form of preheated air, which will be supplied to the furnace, and the rest 1293.2 kilocalorie will be lost to the surrounding. So, if you make the heat balance, so heat input is 6328 kilocalorie. I will write down the heat balance. So, heat input and heat output. So, heat input is sensible heat in POC. That is how you will be doing the heat balance also, 6328 kilocalorie, and there is no other heat input. Now, output, the sensible heat in POC, that is equal to 1293.2, and in percent 20.4%. You see that still 20.4% heat is being lost. Sensible heat in preheated air, heat in preheated air, that is equal to 4402, or that is equal to 69.6%, and heat losses, that is equal to 632.8, and that is equal to 10.0. So, this makes again 6328, and this is equal to 100%. So, why I have given the heat balance? From here you can get a clue what should be done if we want to improve the efficiencies of the regenerator. You know, 20% is going to lose, 10% is the heat losses. Maybe you can do something more in order to improve the design and construction of the regenerator. Now, we can calculate the gross available heat. Gross available heat, that is equal to calorific value of the fuel. As I said, you can calculate from Dulong formula. This gross available heat we are calculating is per kg of fuel. 10,642 plus 4,402 minus 6,328. So, this gross available heat is 8,716 kilocalorie, or that is equal to 81.9% of net calorific value of fuel oil. Had there been no preheating, so gross available heat, no preheating, this will be equal to 4,314 kilocalorie. That means only 40.5% of net calorific value of fuel oil is available. So, you can see the importance of integrating a heat recovery device. You are able to increase the gross available heat almost 50%, and to that tune you will be able to save almost that much amount of fuel if you preheat and if you want the process to be carried out at 8,716 kilocalorie. So, that is, it shows that how integrating the heat recovery devices, in this example we have taken a regenerator, how it helps. It helps in many ways. One way, it helps to decrease the fuel consumption. Had there been no preheating, and if you will be requiring 18%, 81% of the heat, then you have to burn more amount of fuel. Another thing is that whatever heat you are adding or whatever heat you are extracting from the flue gas, you are also reducing the emissions, that is thermal emissions, to the environment. So, this particular example illustrates not only fuel economy, but also illustrates how to reduce the thermal emissions. So, in essence, this example has said to you that fuel economy and thermal emission reduction, this heat recovery is a very, very important thing. Now, let us take another case. Now, let us take case 2. We just extend this example further to illustrate some of the more important things. So, let us take case 2. In the case 2, we consider air leakage. In case 1, mind you, we have not considered air leakage. Now, we are considering air leakage. We consider 15% of theoretical air is leaked into furnace. All other operations are same. We have not changed any other operation other than there is now an air leakage. We are operating the furnace, 110% air, fuel oil is the same composition, and then we are integrating with the regenerator. The only difference between case A and case 2 is that 15% of the theoretical air is leaked into the furnace, and let us see how this air leakage affects the gross available heat and so on, and also regenerator efficiency. Now, what does it mean if the air is leaked? Since you have decided to work with 110% theoretical air, In case 1, all 110% air was routed through regenerator and a preheated air was taken into the furnace. Now 15% air is being leaked into the furnace. Now only 95% of the air will be passing through the regenerator. Could you get the thing which I wanted to convey? Out of 110% total amount of air, since 15% has leaked into the furnace, now the amount of air which will be taken to the regenerator for heating is only 95%. That means 95% of the heat, 95% of the air will now be preheated into the regenerator. This calculation we will do. So, now with the air leakage, the following scene emerges. Earlier we have calculated the total amount of air will be same. The total amount of air now that was earlier we have calculated 0.5236 kg mole. Air leakage that is equal to 0.0714 kg mole. So, now air passing through regenerator, passing through regenerator, how much it will be? You have to subtract 0.526 from 0.074, that will be equal to 0.4522 kg mole. So, now again if I do a block diagram for balance, then it appears as follows. This is the regenerator, and I will make it, this is a furnace. So, in the furnace, air leakage, that is equal to 0.0714 kg mole. Total air is equal to 0.5236 kg mole. So, here only air for preheating will be 0.4522 kg mole, because rest air is leaked directly into the furnace. Of course, here is the flue gas and the preheated air So, preheated air will be only 0.4522 kg mole. That is what it shows it now. So, now for this case, again if we want to calculate the gross available heat, we have to perform the same calculation as we have done earlier. We have to find out what will be the sensible heat in preheated air. Again we are assuming the same thing, relative efficiency is also 80%. Though you may argue, sir, little bit amount of air is decreased, because earlier it was 0.526 kg mole was passing through the regenerator. Now it is 0.4522 kg mole is passing only to the regenerator. velocity of the air will be somewhat lower than the earlier case, the relative efficiency of the regenerator could be slightly higher. It is possible. Then for the sake of calculation, we are considering the relative efficiency same as that was in case 1, that is the 80%. So, let us calculate now efficiency limit. You have to calculate a fresh sensible heat in air at hot flue gas temperature. So, I have given already the values of enthalpy content. So, I am simply writing down 0.357 into 10389 plus 0.095 into 11,000. Heat content in flue gas is the same as that we have calculated earlier. If you multiply it by 100, so you see now the efficiency limit has gone down to 75.1%. Earlier it was 81%. So, as a result of decreasing the efficiency limit, what will happen to the overall thermal efficiency? Overall thermal efficiency, that will be equal to 75.1 into 80 upon 100, that is equal to 60.1%. Now, that means the sensible heat in air, sensible heat in preheated air how much it will be? It will be 60.1% of the heat of flue gas. So, that will be equal to 3803 kilocalorie. So, you can make out what is the effect of air leakage. So, now we can calculate gross available heat to furnace chamber. So, gross available heat, that will be equal to 10,642 plus 3803, that is the sensible heat in preheated air, minus 6328, that will be equal to 8117.2 kilocalorie. Now, so due to air leakage, only 76.2% of net calorific value of fuel is available to furnace. Now, this now slightly less amount of heat will be available to the furnace, and what it will lead to if you operate the furnace at the same amount of gross available heat as that of case 1. What will happen now? Can you think of? Because now the gross available heat in presence of air leakage has decreased, but you want to operate the furnace at the same amount of gross available heat for case A. So, naturally the fuel consumption will increase. So, in this case fuel consumption fuel consumption will increase by around 7%. So, that is what the role of air leakage into the furnace. So, air leakage is a very detrimental to the fuel economy. So, in short we can say that air leakage it will increase fuel consumption. How it will increase? Because whatever amount of air that is leaked into the furnace, it will take the heat of the furnace, and in order to compensate that heat, you have to supply extra amount of heat. That is the one detrimental effect of air leakage. So, for all fuel economy purposes or for fuel saving purposes, it is utmost important that air leakage in the furnace should be as minimum as possible. Now, another important effect of air leakage is when a furnace is integrated with a heat recovery device, then lower amount of air will be passing through the regenerator, through the regenerator and will decrease the efficiency limit. And when it decreases the efficiency limit, naturally it will also decrease the overall thermal efficiency, and as a result of decrease in overall thermal efficiency, the amount of heat which is transferred from flue gas to air will also be lower. So, in fact, the air leakage affects in two ways, broadly speaking. One way, it increases the fuel consumption, because naturally now air is leaking and a part of the heat will be taken by the air to heat to that particular temperature. So, common sense says the fuel consumption will increase. So, therefore, all arrangement must be made so that air leakage remains to a minimum. Another effect of air leakage, when a furnace is integrated with the heat recovery device or regenerator or recuperator, and if the furnace operates with the same total amount of air as it was envisaged in the design stage, then a lower amount of air now will be passing through the regenerator. As a consequence, you are unable to utilize the efficiency of the regenerator also. Therefore, all efforts must be made to see that the air leakage remains to the minimum.